Good morning. It's my distinct pleasure and honor to introduce Professor Naomi Leonard from Princeton. She's Edwin Wilsey Professor of Mechanical and Aerospace Engineering, and she has many honors to her name. She's a MacArthur genius, so you see a genius before you, and she's a fellow of every society that you could be. IEEE and ASME. Anyway, she has many honors. I won't list them all. I think she's one of the very most creative and interesting people applying dynamical systems to engineering in general and intelligent machines and systems in particular. And so I'm always excited about her work. And we welcome you.
Okay. Thank you. So thanks very much. It's great to be here. I'm going to essentially present some nonlinear dynamics for distributed decision making that derive from principles of symmetry and bifurcation. And what I want to do is show you and maybe convince you that these nonlinear dynamics can be useful for advancing both a kind of model-based investigation of decision-making in natural groups like a flock of birds, but also a systematic design of decision-making dynamics for engineered groups like a team of robots. And I'm particularly motivated, I mean, if you think about some of the challenges that we have if we want to enable systems to operate in complex environments, they should be both stable, reliably stable in the presence of disturbance, but also they're going to need to be flexible in how they respond to changes in the environment. And this is something that maybe I will convince you that we can learn from nature, because it appears that animal groups are really good at managing this kind of critical trade-off between being stable but also being flexible. And this is a little bit of motivation from prior work. So where am I here? Okay. So back, I guess this was now 12 years ago, this is work with students and colleagues, a big project where we developed methodology to automate a group of underwater robots. Are called, these guys are called underwater gliders. So they're autonomous vehicles moving around. And the idea was, how do we coordinate them so that they move in patterns? They're taking measurements, say, of a temperature field. What do we want to do? We want to maximize the information and the data that they're collecting, or minimize our uncertainty about the temperature field out there. And so you're looking at data from the experiments. We actually deployed this, and this is just north of Monterey Bay, a 20 kilometer by 40 kilometer by almost 1,000 meter deep volume, just north of Monterey Bay, California. These guys were automated over the course of 25 days. So doing these patterns on their own, dealing with currents. You see the vector field is actually their estimate of what the currents are. So trying to deal with being stable about what they're doing in the presence of disturbance. But some of the ideas that I had at that time were, what if we could make them make a decision on their own to change the plan? Like, okay, something's happening offshore. Maybe they could all move offshore. These are kinds of things that were motivated from this experiment where we collected kind of unprecedented data set. It was kind of unbelievable in and of itself, but you can always ask for more. And I pulled this little video off of kind of like, what more might we be able to do? I don't even know who to attribute this to, but this beautiful video of this school of fish doing what I think of as kind of like a both stable and flexible series of maneuvers, seemingly smoothly. So they're in this incredibly beautiful, circular motion, and then for whatever reason, something presumably has changed in the environment, somebody has detected something, they sort of seamlessly move into this kind of polarized motion altogether. So So my story is, how can we first think about using nonlinear dynamics to understand something about how groups balance flexibility with stability? Then how might we use mathematics and models to think about how to translate that to engineering? How do we endow engineering groups with the same kind of remarkable features that we see in animal groups? But I think my punchline is that along the way, we generate such a rich kind of set of dynamics that we can think very systematically and rigorously about, that it gives us possibilities for both design and going back to the natural systems and thinking about testable hypotheses. So we can kind of advance both of our objectives through a sort of an abstract mathematical framework. And so let me just say that when I talk about multi-agent systems, I'm talking about a collection of individuals, and every individual I'll call an agent, and I'm going to assume that every agent has the ability to sense its environment. Something might include the state of others around it, has some means of actuation can change its dynamics. If it's mobile, it can make itself move on its own, and can on its own decide how it wants to respond to what it senses. So, groups of underwater vehicles or air vehicles, or even, systems in like a wind farm. Everybody, each of these, as long as each agent has a computer and sensors and actuator, you can think about these as multi-agent systems. And likewise, you can think about animal groups like fish school or honeybee swarm as a multi-agent system, because every animal has the ability to sense, change its behavior in response to what it's sensing. But the parallels go further, because if we want to make, say, our engineering systems answer questions on their own, like, has a change been detected in the environment? Which way should we go? Which alternative is true? What action to take? The questions that we're faced with as designers are, how do we design the rules or the feedback laws for the individuals that guarantee, say, stable and flexible decision-making at the level of the group, despite limitations on individuals on sensing and computing or communication. But likewise, in the animal world, here we have these systems that presumably rely on their ability to answer these kinds of questions as a group. And so we want to ask how, we want to kind of go the other way. If we observe these kinds of behaviors, what are the rules that animals are applying such that we see this, right? Despite the fact that they also have limitations on communication, sensing, and computing. And so, we want to do this by coming up with some kind of abstract formulation, that some way to connect, so that we can think mathematically about this and rigorously, and then move between these two worlds and have what we learn in one domain inform the other in a rigorous way. Okay, so what I want to do is start with telling you about two studies of animal groups. I'm going to talk about fish, and then a little bit more in depth about honeybees, and how their stable and flexible behavior reveal what I would call instability as a key to flexibility. And a way to think about that is to think about it in terms of a bifurcation diagram, like this is a pitchfork bifurcation diagram that I'm showing you on the right. And the idea is that this kind of represents a transition from a stable behavior, this might be like indecision, to another stable behavior, like a choice between two alternatives, as say, a control parameter, which would be the independent variable, increases smoothly through a bifurcation point, which here would be the origin, where there's a singularity corresponding to an eigenvalue crossing the imaginary axis. Okay, and these kinds of this is a symmetric bifurcation, appear naturally as a result of symmetries in decision-making dynamics. So for instance, a group that has equal-sized subpopulations that have opposite opinions would be a symmetry, an S2 symmetry, or a group that's making a decision between two alternatives that have equal value. That would be another symmetry. And then the idea is you can study the more general systems as perturbations of the nominal symmetric system. And you can do this actually through a theory called Singularity Theory, which is actually a robust bifurcation theory. And what this does is it tells you how bifurcation diagrams themselves change in the presence of perturbations. So we can understand this kind of transitions from one stable behavior to another, a flexible transition, even in the presence of perturbations or asymmetries. And singularity theory actually, it's called has an organizing principle to it, because what it does is it provides us with an equivalence. So basically it tells us how all dynamical systems that exhibit the same singularity are equivalent, how they map onto one another. And so here's the idea, is that if we can define some dynamics, this sort of abstract model that realizes the same singularity as systems that we're interested in, then we automatically have this equivalence. So through this equivalence, we can use it to kind of map us. We know how it maps between these particularized dynamical systems. And I'm going to take this one step further, because I want to also then say that this, you often think about bifurcation parameters diagram as being something very static, but I want to think about it as something dynamic, because I want to design dynamics for this control parameter so that I can think about, as I increase, say, this parameter, I move from one solution to another as kind of like a controlled adaptive response. And so this is the idea. Let me first tell you about this is a sort of a fish story. So Ian Cousin and colleagues back in 2005 did it was a big simulation study where they were looking at a group of movers on the plane using a very sort of standard model where there were forces of repulsion if your neighbors were too close, and forces of attraction if your neighbors were a little too far. But also there were two subgroups in this population. Half of them had a preference for going, say, due east, and call that 0 degrees. And then the other half had a preference to go in some other direction, and they varied that other direction all the way from 0 to 180 degrees. And what they showed in this plot, so here, the color map, the redder it is, the higher probability that the group moved in that direction from this many simulations. So you're looking at sort of the group direction as a function of this relative directional preference of group 1 in 0 degrees and group 2 going all the way from 0 to 180. And what you see is that when the difference was small, they couldn't distinguish, and they basically didn't make a choice. They split the difference and kind of went down the middle until there was some critical difference, and then they could distinguish, and then with sort of equal probability, because there was this symmetric equal size subgroups, they would go either in one direction or the other, right? Which is kind of interesting. And in fact, when they made asymmetric groups, you got a picture that looked like this. And if you think about it, you can see that it looks a little bit like this pitchfork bifurcation I was just showing you before, right? In fact, it also looks like what we'll get to know as the unfolded pitchfork that I showed you before when there's asymmetry, because there's still the possibility of, some guys going this way, but not as much. Interestingly, Ian then ran some experiments where he trained some fish to know about this sort of yellow source of food, and some to know about this blue source, and he put them in a tank together. And sure enough, this is kind of a dynamic version of this plot as you move along, because when you're really far away, the preferred directions of the two different subgroups the angles are close, but as you get closer, the angles get further apart. And sure enough, they don't decide until they get close enough, and then they pick one or the other direction. Okay, so that's one story. I want to tell you a little bit more about the honeybee nest site selection story, because this is also, and I'll get into a little bit more detail about what I mean about it being flexible and stable. So this is the story of in a honeybee nest when it gets overpopulated. Something like 10,000 honeybees take the old queen, and they they move out, and they have to find a new nest. They sit on this, they gather like on a tree, and something like 300 or 400 of them, 3 or 4%, go out and scout out new nest sites. So a nest site is a cavity in a tree. And the idea is that, what actually happens is that they're able, over a few hours or a couple days, to find a nest site that will be sufficient for, lasting the winter and providing enough storage for their honey. It's kind of unbelievable because they're actually able to pick the best out of N. So they know very well what the quality of a nest site is. It's something like, so it's a cavity in a tree. It should be pretty high up off the ground. It should be something like 40 liters in volume. The opening should be something like 15 centimeters squared in area, and it should be facing south, and it should be low in the cavity. And so the process is kind of incredible. So how do they do this, right? How do all these bees do this? It relies on something called the waggle dance, and this guy, Carl von Frisch, wrote about this. He actually won the Nobel Prize in 1973 for decoding this waggle dance. So this waggle dance goes as follows. A bee, she scouts out a site. She comes back on the vertical part of the swarm. She does this dance. So this is a snapshot of what it looks like. And this is a little cartoon. So she's making these little closed circuits, and on the kind of this part, this diagonal part, she's vibrating her abdomen. Okay, and by doing this dance, the waggle dance, she's able to communicate the direction, the distance, and the quality of the site that she's just scouted out. So she's advertising and trying to recruit. So essentially, this is kind of crazy. The angle relative to gravity is, here's von Frisch's picture from the Nobel lecture, is the angle, the azimuthal angle from the site to the sun. Yeah, it's really incredible. And then the number of vibrations of her abdomen is proportional to the distance. And then the liveliness of the dance, kind of like how quickly she makes these closed circuits, and the number of dances tells you, the quality. So, like 100 if it's a 5-star hotel, and, many fewer if it's a, cheap motel. But then you might ask, okay, well, that's great. So these advertising, this von Frisch's student, Martin Landauer, did these experiments actually running all over Munich, and figured out how the bees then deliberate based on this. So what happens is, let's think about 2 nest sites, A and B, and let's call VB the quality, the value of B, and it's greater than VA. So we have this one site that's better than the other. So a few of these will start to go out. They'll scout, they'll sort of commit, they'll come back, they'll do their dance, they keep going back, although, and they're trying to recruit, although if they keep going back and nobody's there, their commitment will decay, but others will become recruited, and so, if it turns out to be a really good site, more will gather there. And then what essentially happens is that when a quorum is reached, meaning if any time a bee goes to her site and she sees something like 25 or 30, that snapshot of 25 or 30 tells her that enough of them have decided. And so by quorum, those will go back, and then they use another signal called piping, and they basically say, hey, guys, we've all decided. And everybody says, okay, fine, and they go. So they don't actually wait for unanimity. We actually got interested in this problem after this paper came out. So this is Tom Seeley, who does experiments on an island in Maine, and he was studying, along with colleagues who were developing models, an additional signal, which turns out to be really interesting, and it turns out to tell us that these bees not only pick the best of N, but they're also able to deal with equal value sites, right? Because that's a hard problem to do both, right? You want to choose the best of N, but what if they're equal or near equal? You don't want them to deliberate forever. You want them to make a choice, right, in a timely way. And so it turns out there's this extra signal. It's called the stop signal. It's like the shut up signal, because what they do, so here's like one who's, committed to B, essentially headbutting one who's dancing for A. And it has this nice tempering of the dance and getting the decision moving along. So you can also think of it as a cross-inhibition. In fact, you can see it. This is the model. This is a mean field model that Tom Seeley's colleagues developed. It's in their science paper from 2012. So here, they're looking at a very large population. So YA is the fraction of the population that's committed to A. YB is the fraction committed to B. YU is 1 minus YA minus YB. So it's the uncommitteds, right? And so this looks at the evolution of YA and YB. Here's the decay term. And that's inversely proportional to the value. Here's the commitment term. So that's an uncommitted becoming committed to A, proportional to the value. Here's the recruitment, and A meets an uncommitted. And then here's this stop signal, right? And we're going to assume, or they assumed, that everybody is using the same rate of stop signaling. That's the sigma, and that's going to be a really important rate for us. So let me just show you what the model, how the dynamics evolve, right? So these evolve on the simplex, right? Because YA plus YB plus YU equal to 1, right? So this vertex corresponds to YU equal 1. This corresponds to everybody for B. This corresponds to everybody for A. These are like little quorum thresholds. And in this example where B, like we saw before, where B is better than A, I'm just showing you a whole bunch of solutions. You can see that they sort of quickly converge to this one-dimensional manifold, and then there's only one stable solution for B, and everybody goes there and makes a choice for B. Okay, so that's very fitting with what we've seen. But we got interested, so this is with my former student, Darren Peiss, at what happens, in this case when they're equal value alternatives, because this is the experiment they did in this 2012 paper. So here's the same dynamics, but VA is equal to VB is equal to some V, okay? So now look at these two plots, same thing. I'm just simulating here for you a bunch. In both cases, the values, the equal values are the same, but what I've changed is how much stop signaling they're doing. They're doing a little bit on the left and much more on the right. So on the left, look what happens. The stable solution is at complete deadlock. Half the group is for A, half the group is for B. They're not choosing, right? On the right, that becomes unstable, so that's what this hollow circle means. And we get these two stable, sort of symmetric situation, equal values. There's a symmetry. And so now, depending upon initial conditions, they'll either go here or they'll go here. Pretty cool. In fact, it gives us what we might expect, this pitchfork bifurcation. So what I'm plotting for you here is a projection of the solution. So when it's up at 1, that means everybody's for A. When it's down at 0, it means that everybody's for B. And I'm plotting for you the solutions of that equation as a function of this stop signaling rate, right? So blue here is stable, red is unstable. And when sigma's small, they're undecided, like we saw. When sigma's large, you get indecision being unstable and a choice for one or the other of the alternatives. It gets even more interesting, and this is, I think this is already fantastic. Turns out that, at least according to the model, the critical value, the bifurcation point, is like inversely proportional to the value, okay? So that we call this value-sensitive decision-making. So they're not just looking at relative values, they also, how incredible is this? The B's are making their choice when they're debating over equal or near equal sites. That depends on how good they are, not just that they're equal. So if they've evolved to have a stop signaling rate that's kind of let's say here, right? Then the bifurcation point, if they're two not so good sites, right, the bifurcation point moves to the right, right? So now they're going to be at indecision. They're going to wait for a third alternative to come along, right? Let me show you another way to view this. Okay, so here is value as a function of stop signaling, okay? So we're looking at V equal 5. So we're looking here, right? So if stop signaling is low, we get a solution at deadlock. If stop signaling is high, we get this, a decision for one or the other alternative. But see, this is the inverse curve of, this is the sigma star, the critical value. So for poor value ones, I need to do an awful lot of stop signaling in order for this to work. So if they've evolved to say, if stop signaling of a certain fixed value, then they're essentially kind of adapting to what's going on. Kind of incredible. But, so why not think about, if we're thinking about design, wouldn't it be great if we could make this happen and think about sigma as a control parameter? We could change it. We could say, all right, wait for your, a third alternative, but okay, it starts raining, now you got to make a decision. And so you could do something like crank up sigma. So here's just like a little example where I'm going to show you a simulation where I'm just linearly ramping up sigma, and I'm going to go through the critical value. And so it's going to be like moving, like I said in the first picture, moving along indecision and then flexibly, because something's happened in the environment that's triggered my cranking up of sigma, to make a choice. And so here's just a little simulation, equal value alternatives. We've added some noise to the rates just to make it a little more realistic. And you can see that at the beginning they're undecided, but as soon as sigma gets hard enough, here they happen to choose A. Okay, so that is some motivation for what's to come. But also, I told you, okay, we're not, in real life, things are never going to be perfectly symmetric. So what about when there's asymmetry or other kinds of perturbations to your beautifully symmetric system, right? Because we want to think about this as our nominal system, and then what we study in real life are the perturbed versions. So now I'm going to think about a delta V. So we've been studying delta V, which is VA minus VB, being 0. That's our perfectly symmetric case. So what happens if one is better than the other? We get this unfolded pitchfork. Okay, you saw it on my first slide. You saw it in the schooling fish, right? But it shows up here. And in fact, what I'm going to show you and tell you is that the singularity theory would have told us this exactly. There's actually a very small number of possibilities that can happen with the introduction of asymmetry, and this is one of them. And so you can see here what happens is, this, A is better, so, that's always a stable solution, but I get this other, sort of far away, it looks like the pitchfork, but nearby, A is dominating, right? So it's, if I have an initial condition inside here, yeah, I'll choose B, but otherwise I'm gonna choose A. Also built into just the fact that there's this pitchfork bifurcation is this, what I think about is like a robustness to fluctuations in delta V. This is really important, right? We don't want the group to choose A and then quickly switch to B if things are fluctuating. So this hysteresis is also kind of fundamental to the pitchfork bifurcation. So what you're looking at is the decision now as a function of delta V. So suppose delta V is positive and I've chosen A, but suppose A starts to dwindle or maybe B gets a little bit better. What this says is that I'm not going to switch right when delta V is 0 or just slightly, it has to be significant, sufficiently changed in order for me to jump down and pick the other alternative. So sort of, we got this flexibility and we've got this robustness, kind of incredible. And so, for me, this is kind of a launching off point, right? It doesn't answer all my questions. For instance, this is a mean field model, right? So I can't ask questions about, like, what's the role of the network structure? Who can see whom doing the dance? What's the role of heterogeneity? What if some of them have just stronger signaling than others? And those are the kinds of questions that we want to ask for design, because we want to design for individuals. And in the fish, it's a simulation model, so it's very hard. They draw this picture with this critical value, but what does that critical value depend on? I can't just rely on simulations to create a systematic design methodology. Okay, so singularity theory, where does this come in? So here's this idea. This is sort of the general theory, and if you're interested, there's this not easy to read, but if you're patient and persevere, book by Marty Golubotsky and Schaefer from 1985. But I can sort of summarize the story, and then I'll show you, make it clearer through the pitchfork example. That you start with your nonlinear dynamics and you reduce your study to a scalar equation, basically where you're looking for solutions to your dynamics. So it's the scalar equation G is equal to 0, where Y is like a reduced state, right? And lambda is some kind of, control parameter or bifurcation parameter. And essentially, to get this Lyapunov-Schmidt reduction, what you're doing is you're projecting in the direction of a 0 eigenvalue at a singularity. So singularity here is your non-hyperbolic equilibrium. Okay, and so then once you've done this, once you've kind of found your G, the theory allows you to do a whole bunch of things. First, you can use the theory to determine of what qualitative type is your G, what equivalence class. And then it gives you this kind of classification of all these different classes. It tells you, all these properties. And one of the most beautiful properties is this enumeration. It's called the universal unfolding. The enumeration of all kinds of perturbations to G, right? What happens when you introduce some kind of perturbation? And so essentially it tells you that, my system of equations in its reduced form, if I add a perturbation, that's going to be equal to some k-parameterized function, capital G, which when these parameters, alpha 1 through alpha k, are equal to 0, I just get back my nominal solution equation. But for any kind of perturbation, small perturbation near the singularity, I can find some set of values of my alphas. So I can parameterize all these perturbations by this set of alphas. And let me just show you what I mean in the case of the pitchfork. So in the case of the pitchfork, if you have your system and you've reduced it down to this equation for solutions, then these are the conditions you have to check. So these are just derivatives, second derivatives, third derivatives, and whether they're equal to 0, whether they're positive or negative. You check those conditions and then you're done. Then you know that your G is mappable. It's equivalent to, this is the normal form for the pitchfork. So all systems that reveal a pitchfork are transformable to this normal form, right? This is the pitchfork that we saw before. Here y is the variable, lambda is the control parameter. But it also tells us what the capital G is. And it's called a codimension 2 bifurcation because we have two parameters, alpha 1 and alpha 2, that parameterize all possible bifurcation diagrams that we can get when we add a perturbation. And these are the four. So this is alpha 1, alpha 2, the alpha 1, alpha 2 plane. So for any perturbation, I get an alpha 1, alpha 2, and then I can find out where I am on this plane, and this tells me which unfolding I get. And we've already seen these two, right? And these are kind of variations of the theme. You just got this little extra sort of hysteretic story. Pretty neat. Okay, so that's the idea. I mean, can we now design? I'd rather have not a mean field model. I want an agent-based model. Can I design an agent-based model that's sort of abstract and kind of refinable enough that for which I can find my G and presumably my capital G using this singularity theory, Lyapunov-Schmidt reduction, singularity theory. And if I can do that, and if it's recognized as a pitchfork bifurcation, then I should be able to connect with these animal groups, right? Because they all have their G's, right? So now I know how this maps onto this. So I can go and ask questions from my model about these evolved systems. I'll have a prediction, and I'll see if we can test them and understand whether or not they make sense in the real natural world. Whoopsie. And I can also use it for design, right? And I can connect these different particularized systems. So if I learn from one, I can presumably translate to the other. So we can come up with a sort of a big, here's like a big view plan of what we might like to do, right? We could think about a system with n agents, m options. You might think about, like, if I'm an agent, I could have opinions about all these options. Let's say that my opinions sum to 1. So if I have two options, half for one and half for the other would be my neutral state, but it would live on the simplex. I can change coordinates and linearize. I like to work with the neutral point being 0. So now it would be kind of like positive for one and negative for the other, and 0 being neutral. And then I can talk about symmetries. So perturbation symmetries in the agents, right? So the symmetric case would be sort of indistinguishable agents. Permutation symmetries in the agents. Permutation symmetries in the options, indistinguishable options. That's my symmetric story. So these commute under the action of Sn cross Sm. I get this neutral solution to be a fixed point. And so then here's the idea. You decompose the tangent space into like agreement and disagreement, right? And then you think about the actions of these symmetries, and basically you can get the whole kind of normal form story. What are all the possible solutions, the possible bifurcations, the possible unfoldings? can get very, very, very complicated. So I'm going to stick to, first I'm just going to talk about one S2 symmetry in the options, and then I'm going to talk about an S2 symmetry in the agents and S2 symmetry in the options, right? Which is going to allow us to talk about how groups agree, how they disagree, how they do things in between. But one of the big questions, and one of the things that we've been working on is, well, how do I write down a vector field, a set of equations, nonlinear dynamics that would provide the control, the dynamics for these systems that realize kind of the richest possibilities out there, right? Allow us the richest kind of flexibility. And I'm going to show you that it's sort of even more than we anticipated when we went in. So this, the first stage, this S2 symmetry, so this is joint work with my collaborator, Alessio Franchi, who is a professor of mathematics at UNAM, the National University in Mexico City. Vaibhav Srivastava is a former postdoc. He's an assistant professor in Michigan State, and Beck Gray, who's a current graduate student. So we're looking at n agents, 2 options with this kind of S2 symmetry. Each agent has an opinion. So we have n agents. If it's for A, its opinion is positive, its state is positive. If it's for B, it's negative. If it's equal to 0, then it's perfectly uncommitted. And we'll think about like how the group decides by just looking at the average of the individual opinions. So that's Y. And we're gonna be concerned in this first step about agreement. Next, I'll talk about disagreement. But so here, this delta, so YSS is just the steady state value of Y, and XSS is just the steady state vector of opinions. And basically, delta is equal to 0 if everybody's either perfectly uncommitted or opinions are all positive or the opinions are all negative. Okay, so I want to write down these dynamics. So I can write down conditions for which I need to find my vector field. So I want to write down the right-hand side of this equation. I want to find Fi for every Xi to basically do what I've just said, make indecision my neutral stable, my neutral equilibrium. And I want to make the pitchfork happen for some value of my control parameter, which is called U here. Okay, so I want indecision to be an equilibrium for all values of my control parameter, and then I want symmetry in the options, right? This S2 symmetry, and remember, positive for A, negative for B, so that means an S2 equivariant vector field, so I want minus F to be equal to F of minus X. I want to be able to make those, I want to be able to swap options. I also want there to be a singularity at indecision, right? That's my bifurcation point. So that means I want the Jacobian of this vector field at 0 to be singular for some value of U star. So here's where things get interested for those of you who think about consensus dynamics. I'll show you that in a second. We're going to make use of those kinds of dynamics. But I also want my agents to agree, okay, so in this setting. So here's the model. Here's the model. Very simple looking. So here are the dynamics for the opinion of the ith individual. This is like some kind of fixed preference. Like I go into this, or maybe it's some information I'm getting from the environment as positive for A, negative for B. Then this is like my little negative feedback. So here, Aij is the weight that I puts on the information it's getting from J, and Di, it's like the integree. It's all the information, the sum of the weights of the information that I'm getting. So you can think about if these are all 1 when they exist, this is just the number of neighbors I have. So if there's no preference and this term is 0, then I just decay to no opinion, right? Because I have no reason to pick one or the other. So this other term is a positive feedback term, right? So here is I'm sort of summing up this function of the opinions of others with these weights Aij. So this is a sigmoidal function, right? So looks something like this. So we're basically saying, okay, you can scream as loud as you want, but I'm going to cut you off at some point, right? So it maxes out at 1 and at -1. But U is kind of a dial, right? So I can crank up how much I'm yelling or having everybody. It's like a social effort, my opinion out. And so what I want you to think about here, so if you want to just think intuitively of how we create a pitchfork bifurcation, is this interplay between negative feedback and positive feedback. So you can imagine if I crank up positive feedback, I'm going to send an eigenvalue over the imaginary axis. And that's exactly what happens. So this is just the vector version of those equations. And let me just show you that, I mean, you can kind of see these are both odd terms. So this symmetry is really easy to check. Singularity, so this is what I was referring to. If I take, so let's look, so I'm going to look at the symmetric case when beta is equal to 0. And if I look at the Jacobian at this neutral point, this is what the matrix looks like, right? So actually you can see this sort of interplay that's being regulated by this control parameter u, the negative versus positive feedback. But when u is equal to 1, this Jacobian is just minus the Laplacian of this graph, this network, right? So for those of you who work on networks, you know that for a connected graph, this has 1 0 eigenvalue, right? So that's our singularity. We get it. We get it. And what it's also super beautiful about it is that like the center manifold tangent to this 0 equilibrium is the consensus manifold. It's the vector of all ones when all the xi's would be equal to one another. Everybody would agree. So what we're actually doing is creating a pitchfork bifurcation that lies on the consensus manifold where xi equal xj. Okay, that's what that gray plane is meant to show you. And we can prove all this actually using Lyapunov, Schmidt reduction, and this singularity theory, right? So we can take these dynamics, we can do the reduction, which gives us our G, and it gives us our capital G, and we can prove essentially that when beta is equal to 0, we get, when u is less than 1, we get just the single globally stable equilibrium point. When u is greater than 1, we get two stable solutions, and indecision becomes unstable, and we can solve for those. But when we introduce the perturbations, because we computed this G, the capital G, we can see really interesting things that we won't be able to see with the mean field model. So this, for example, tells me how the bifurcation unfolds as a function of each individual i's preference. So I can see, whether it pushes me towards A or towards B, and who has more influence, because the sort of the gradient of G with respect to the ith guy's preference is equal to, this is like the eigenvector centrality. It's the ith element in the left eigenvector corresponding to the 0 eigenvalue of L. Okay, so I'll show you that in a second. We can also extend this to the case where not everybody has like a global Q for U, that everybody has their own control parameter. Okay, so here, let me just illustrate this, and you'll see all these stories. So this is, I don't even know how many there are there, maybe something like 12 individuals, some network, nobody has any preference, we get the perfectly symmetric case, right? Everything's symmetric here. Then I introduce some preferences. So 4 of them are for A, and 3 of them are for B. And as you might expect, we get this unfolding, which we know we should get. And here, y high is positive again is A, so they're all going for, not all, but the stable solution throughout is for A. We also get that hysteresis, so we're building in this robustness as well as these kinds of flexibility. So, we get this now, this kind of robustness and fluctuations between these preferences. So if, like, you're sensing something in the environment, it's getting a little bit smaller, we're not immediately going to, we're not going to, jitter back and forth between our alternatives. And so this is what I was talking about. We can understand, based on the network structure, how the influence of those who have preferences is going to affect the decision of the whole group. So Beck just took this graph and messed with it, but in such a way that the sum of the eigenvector centralities of the 4 ones for A is now less than the eigenvector centrality of the 3 for B. And so now the solution for B is the one that's much more stable. And that's something we could predict. I mean, that could be something that we could test, right? But we could certainly design it in if our robots are using these kinds of rules. I mean, here's something else interesting. This is another symmetric case where like 4 for A, 4 for B, and they're only, this is kind of like an all-to-all, but just with these 4 who have no preference. So there's like a buffer between these two biased groups. And it's still very symmetric. But what's interesting is when beta's equal to 1, we get our old pitchfork, but when beta grows, we get another kind of unfolding. This is a subcritical bifurcation, pitchfork. And if you think about my story about giving dynamics to this U, this control parameter, you know, this would be kind of a soft decision, right, as I move U. This would be a much like a sharp decision. I'm moving along and boom, I jump up and make a decision, and then I'm moving along and boom, I jump down. So it's more like a switch. So there's all kinds of things that one can craft here. We can recover this value-sensitive decision-making. So here's a group. In this example, it's an all-to-all connected group. N of them are for A, N of them are for B, and the remaining guys have no preference, and we can actually write down an approximation of what the bifurcation point looks like, and you know, it's sort of like analogous to looking at our old sigma star, because we get this 1 over V, but we also can see the influence of scale. That's not something we could have looked at in the honeybee story. So N is the total number. We can look at the influence of how many don't have a preference. And we can see things like as we, you know, they get better and better, yeah, the bifurcation point moves to the left, makes it easier to make a choice. It also becomes steeper, so we can start to measure kinds of things. So it's going to be a quicker towards, if we have like a quorum threshold. Whoops. We can see here, this is for a fixed number of individuals, that I'm increasing the number that don't care, right? And that's dropping the curve, making it easier again to make a decision for a given value. Something that's super interesting that we've studied actually with Ian with the fish. Here is an example of how we might implement this if we have these autonomous robots in the field and they only have their own UI, not a global UI, and suppose they have some kind of rule that says, okay, you know, start thundering, we've got to make a choice now. How might they deal with this? Because they don't know where everybody is, they don't know what everybody's opinions are. So what we've had them do here is estimate what they think the average opinion of the group is, and then drive their U up until its magnitude meets the magnitude of some threshold when they've made a decision. So here's a little simulation of that. So the black lines are showing the xi's as a function of, this is the average of the ui's, and the green shows the average of the xi's, which is the group decision. So you can see that more were for A than for B at the beginning, but they all kind of coalesce at something close to, I mean, it looks like it's at 0, but of course it's converging towards 0, and it must be, you know, throughout this whole time a little bit above 0, because then after it passes through the bifurcation, it makes a choice for A, right? But no individual could have known that without having to kind of take advantage of this kind of algorithm. There's another really interesting story, because we're making this happen slowly, so there's an interesting delay when you have like a 2 time scale separation and a singularity. Okay, so this is the grasp lab. So I have to show you some robots, right? So this is basically an implementation of that in my one of my labs with just these little tiny wheeled robots. But we're using theater lights like color to indicate the environment. So these are, so I'm just going to demonstrate this with 2 robots. This purple light that you see is a mixture of obviously blue and red. The red guy essentially is going to have a signal. It's going to measure the intensity of the red light, which is going to give it a preference for moving to the left. The green is going to measure the blue light, which is going to give it a preference to moving to the right. Right now it's purple, and so they basically have equal preferences. So this is the symmetric case, and we see the symmetric pitchfork. The So the floor, think about the floor as going into the page, that plane, and think about the bifurcation diagram as vertical, right? So you're going to just see these guys moving in this plane because this is the decision direction. So this is an individual's opinion being 0, this is being positive, this is being negative, this is choosing to go over here, this is choosing to go over here. So let me just, maybe I'll just run it and explain it as we go. So first, U is low. There's only one stable equilibrium for kind of being at home base. Then something happened in the environment and U jumped up. It's like there was a burst of lightning. And so now there are these two solutions. Wherever they landed after they did their little foraging gave them an initial condition that clearly pushed them to go to this side. Right? So they get there, they do their thing. Now they're happy and they go back to home base. And you can see the little arrows are indicating that they each have preference for one side or the other. So it's like the betas are equal and opposite. They do this.
Naomi, your consensus manifold is equilibrium, but you don't have equilibrium in the configuration space? It looks like that's like configuration space.
Okay, so we've just imposed this little dance that they do, just to give them a little activity when they get there. I mean, otherwise it's boring. So here's another example where we break symmetry. So now I'm going to fix U, right? Let's just assume they're set. They have some U that they're going to use forever. So now it's really just the environment that's changing their betas. So now the light starts blue, and so only this guy has a preference. The other guy has no preference, right? So the green guy wants to go to the right. And so this is the unfolded bifurcation, right? You see this is the stable solution to the right. So at this point, there's only one solution, so they should go there, right? And they do. Of course, the green guy goes faster. Red guy's getting dragged along. And then, whoa, the light changes. And so now, blue doesn't have a preference, and red wants to go to the right. There's only one equilibrium, and they go over there. Right? It gives you a flavor of the kind of things that one might be able to do. But let me tell you just the final little story. So the final little story is, this is, again, with Alessio and another newer PhD student, Anastasia Vizyaeva, and we're looking at two options again, but now two agents. So think about maybe we have a big population, but we're going to look at one representative from two different subpopulations, okay? And each has an opinion. Now I'm calling it theta, positive for A, negative for B, uncommitted if it's 0. And so here are the dynamics that we designed, Anastasia designed, right? Looks kind of busy, and I'm going to get rid of some of these parameters in a minute, but here's the decay term, here's the same term, so this is this guy reacting to the other guy's opinion. These are all just some constants. Here's the sigmoid. Here's the new term, right, which is some kind of sigmoidal function of some weighted difference between the two opinions, okay? So now we're going to start to get some interesting stuff. These dynamics have symmetry in the options, like we saw before, positive and negative. We just have to flip the sign and show the vector field flips. But they also have symmetry in the agents, right? So you can flip the agents and just flip the vector fields. Let me just say that this ratio of C to B, those variables don't matter, so we can set B equal to 1. I mean, you can scale everything at the end if you want to go back and put these parameters in, but it's helpful just to set some of them to constants. There's some conditions to make sure we get our singularity. This is kind of important so that we get the range of all the rich dynamics, but this is easier to look at, right? We only have two parameters now, C and alpha. Alpha is going to be like our bifurcation parameter. C is going to be this super interesting parameter that's going to allow us to explore this kind of unbelievable space of possible bifurcation diagrams. So the first result we have is that for all possible values of C, these dynamics, if we basically, they're equivalent to this other kind of symmetry called Z2 plus Z2, which gives us this whole array of solutions. And let me explain that. So if you switch coordinates. So let X be the average opinion, Y kind of the average difference of opinions. So then X-axis is the agreement space, because Y is 0, theta 1 is equal to theta 2. And Y-axis is disagreement space, right? Because theta 1 is equal to minus theta 2, right, on that axis. Then you can show that the dynamics they have the symmetry and reflections about the X and Y axis, and that's the Z2 plus Z2 symmetry. And that means that they're equivalent, so this is all using singularity theory, to this normal form. We see these other parameters, M and N, they're called modal parameters, and they're super interesting in the following sense. So here, lambdas are bifurcation parameters, it's just related to our alpha. But M and N can be described by the single parameter C. And these modal parameters do the following. They basically, just kind of like the alpha 1 and alpha 2 did before for the pitchfork, they basically tell us all the topologically distinct dynamic regions that we have. So for instance, in this quadrant, the bifurcation diagram looks like this, where we have agreement and disagreement both stable. In this region, disagreement is stable, agreement is unstable. In this region, agreement is stable and disagreement is unstable. And we get this sort of mixed mode. Here are the phase planes associated with this. But the result, the second big result is that by increasing C, we can explore all of these except 5, which is not interesting. Everything's unstable. We can explore all of these regions. So with just this one parameter, if I give it dynamics, we can create systems that agree and disagree in response to something that's triggering C. So for instance, here's a little simulation that Anastasia made where we start here, where disagreement is stable. We traverse here by increasing C, and we land where agreement is stable. So here's C down in this region, ramping it up, and then it lands in this region. And here's what the agent's opinions are doing. First, they're disagreeing, because they're in this region, and then they're agreeing, just by moving this simple parameter. So this, to me, is a flexible and stable transition. We're going from something that's very stable and robust to something that's very stable and robust through a single parameter that could be triggered by something in the environment. So this is like, you know, an allocation problem. Okay, I'm gonna go here, you're gonna go there. Okay, something's changing the environment. Now we're gonna both go here. You know, I'm gonna listen to, you know, somebody on the phone and drink my, but now I have to use 2 hands to drink. You know, I can think about it in lots of these ways, including, so I just wanted to put a little pitch in for this work that my group, we're doing with, in the arts. So we're exploring these very same ideas, thinking about nonlinear dynamics and control and decision making in the context of, this is in the case of an improvisational dance. So where we look at models, we think about the role of parameters that might be design dials in a choreographic sense. And this was a piece in collaboration with a choreographer and composer at Princeton that was premiered back in 2016. And there's a paper that's going to come out soon on it, in case you're interested. But I think I'm just about out of time. So, you know, learning from nature, I think, is spectacular. Symmetry, bifurcation, nonlinear dynamics have an important role to play, especially in this thinking about stability versus flexibility. So I want to thank my research group, my funders, and my husband, Tim, and daughters, Amara and Lily. And thank you.
For the spectacular work in talking. I think we have
1 minute, sorry.
One question.